Hello everyone, I'm Malka Jangir from IIT Kanpur. We are studying the course Basics of Materials Engineering and today's lecture is on imperfections and solids. So we'll be continuing from previous lecture. So this is your course offered by Professor Ratna Kumar from Department of Mechanical Engineering, IIT Madras. Now, firstly, we'll be going through some sample assignment questions and then we'll be going through some notes which will be helping you in solving your assignments. So, first question is identify all the favorable conditions for the formation of a substitutional solid solution. And your options are difference in the atomic radii between the solute and the solvent atom is less than 15%. Some crystal structure for the solute and solvent atoms and greater difference in the electronegativity of the solute and solvent atoms or negligible difference in the electronegativity of the solute and solvent atoms. So your answer will be all three except greater difference in the electronegativity. Now the favorable conditions for the formation of substitutional solid solutions are given by Hume-Rothery rules. And in first condition is difference in the atomic radii between the solute and the solvent atoms is less than 15%. And second is same crystal structure should be for solvent and solute atoms. And there should be negligible difference in electronegativity of solute and solvent atoms, because if it is higher then it might lead to formation of some intermetallic components. And fourth is metal will have more tendency to dissolve another metal of higher valency. Second question is okay, so second question is which is not a strengthening mechanism. Options are precipitation, work hardening, creep and solid solution. Answer will be creep. Now we can explain this by saying that firstly for precipitation, the formation of precipitation leads to the strengthening of material, and the work hardening corresponds to the formation of dislocation multiplication leading to enhancement in strength, and creep is a mechanism corresponding to softening of material at higher temperatures. So it is the only one which is not a strengthening mechanism, and formation of solid solution also leads to strengthening of matrix metal. Now third question is which is not a 2D lattice defect. Your options are grain boundary, twin boundary, stacking fault and void, and your answer will be void. Now grain boundary, twin boundary, stacking faults and twist boundary, these all are 2D defects. So as their dimensions are in 2D, so they have length and they will be having an area to them. Compared to void, they'll be having volume. So voids, porosity and precipitates are 3D defects. Vacancies will be your 0D defects and dislocations will be 1D defect. Now what is the slip system for FCC crystal? Your options are 111 and 111 type of your plane and 1 bar 0 type of directions, and 110 type of plane and 1 bar 11 type of direction, 321 plane and 1 bar 11 direction, or 0001 type of plane and 112 bar 0 direction. Answer will be A. Now from here we can see for FCC such elements such as copper, aluminium, nickel, silver and gold, the slip plane will be 111 type and slip duration will be 1 bar 0. So there are 4 such planes and 3 such directions. So 4 times 3 will be 12. So they have 12 number of slip systems. And these 110 and 1 bar 11, these will be, and 321 1 bar 111 will be for BCC type of crystal structure as shown here. And the bottom one is for HCP type of crystal structure. Now, which statement is incorrect? Your options are grain refining reduces toughness, precipitation hardening requires solution heat treatment and aging. Third is work hardening leads to dislocation multiplication, and presence of lattice strain interaction between dislocations and impurity atoms increases strength. Your answer will be grain refining reduces toughness. So this one is incorrect. Now we know that in case of grain refining is the only strengthening mechanism which doesn't reduce toughness, because in case of grain refining it doesn't reduce ductility and also increases the strength. So both are combined, they make it higher, tougher material. Now second is in the process of forming precipitates, quenching from single phase region which is called solution heat treatment and subsequent aging is required. Third is work hardening leads to dislocation multiplication. So work hardening leads to dislocation multiplication due to the formation of form breed sources or because of some dislocations, existing dislocations, or because of some precipitates present. Now in the case of solute solution, the presence of solutes and impurities leads to lattice strain which react with the dislocations, providing a barrier to easy glide leading to strengthening. Identify all the correct statements. Now the magnitude of the grain boundary energy decreases with the orientation misalignment between neighboring grains. Grain boundaries are more chemically reactive than the grains. The total interfacial energy is lower in coarse grain materials than in fine grain materials, or all of the above. Your answer will be the middle ones. So we can explain the first statement is incorrect because the magnitude of grain boundary energy increases with the orientation misalignment between neighboring grains, because with increasing theta your bond length will be increasing and the energy will increase. For second statement, grain boundaries are more chemically reactive than the grains because of higher energy due to deviation of bond length from equilibrium. And third is the total interfacial energy is lower in coarse grained materials than in fine grained materials because of less grain boundary area per unit volume. Now seventh question is identify all the correct statements. First is in a screw dislocation, the atoms distort along a dislocation line, and in screw dislocation the dislocation line moves in the direction perpendicular to the applied shear stress, or screw dislocation imparts shear, tensile and compressive strain in their vicinity, and a screw dislocation qualifies as a interfacial defect. So the bottom two are incorrect statements because a screw dislocation imparts only shear stress, it doesn't impart any tensile and compressive stresses, and a screw dislocation qualifies as 1D defect. linear defect rather than interfacial defect. Interfacial defect will be your grain boundary, stacking faults and twist boundaries, etc. So as shown here, this is what your screw dislocation will look like. Now 8th question is a numerical. So in this, an aluminium alloy has yield strength 145 MPa. It is an average grain size of 2 micrometer and the whole constant depicting resistance to dislocation is 70 MPa. If the grain size is reduced to 100 nanometer, what will be the new yield strength based on Hall page relation? Your options are 226, 405 MPa, 105 MPa and 358 MPa. Now your answer will be 405 MPa. So for this you have to use Hall page relationship. This is simply sigma y is your yield strength equals to sigma naught plus ky d times root 1 by root d. So here your sigma y is yield strength, sigma naught is your frictional stress opposing motion of dislocation, ky is extent to which dislocations are piled up, so it will depend on your strain hardening. So these two, sigma naught and ky, are two constants, so we can find their value. One's value is already given here, so 70 is your sigma naught. Okay, so you have to find out ky using initial parameters, then we can put all the parameters and find out sigma y at the 100 nanometer grain size. So firstly you have to find out ky. So for this we'll be putting 145 equal to 70 plus ky upon root 2. So from this we'll be finding out 75 multiplied by root 2. So sigma y will be, in case of 100 nanometer, will be using the diameter, your grain diameter as 100 nanometer. So when we'll be keeping this, we'll be getting 405 MPa. Now 9th question is identify all the correct statements. First is dislocation movement is favorable on planes with highest planar density along the directions with highest linear density. Second statement is HCP metals are less brittle than FCC or BCC crystals as they have fewer active slip systems. Third is deformation by twinning is usually accompanied by crystallographic reorientations. Fourth option is all of the above. So your correct statements are 1 and 3. This statement is wrong because in case of HCP we have only 3 slip systems. We have one basal plane in 3 directions. So by multiplication you will be finding out there are 3 slip systems. So a system which will be having less slip systems will be showing brittleness. So fewer slip systems result in less plastic deformation in HCP crystal, and higher planar density leads to less lattice friction, which leads to easy dislocation movement. Third statement is twinning leads to crystallographic reorientation. So this is also correct. Identify all the correct statements. So first is Hall page effect refers to strengthening by grain size reduction, the presence of lattice strain interaction between dislocations and impurity atoms. They increases the resistance to dislocation movement. Third is the resistance to dislocation movement by other dislocations increases with the dislocation density. And fourth is all of the above. So your answer will be all of the above because all of the statements are correct regarding these strengthening mechanisms. Okay, now we'll be going through some lecture notes. So firstly, in last previous lecture, we studied about the point defects. Now we'll be moving on to linear defects. So linear defect is mainly dislocation. So these can be screw dislocations, edge dislocation, and mixed type of dislocations. So a dislocation is a linear or a one-dimensional defect around which some of the atoms are misaligned, and within the region around the dislocation line there is some localized lattice string. So as seen here, there will be presence of half planes in case of edge dislocations. So these half planes will lead to the this type of strains that are here. So here it is compressive type of stress because it is this atomic distance is lower compared to equilibrium distance, and here below this dislocation line there will be tensile type of strain because the distance between atoms is higher compared to equilibrium distance. Now the atoms above the dislocation line are squeezed together. Here they are squeezed and below they are pulled apart. The magnitude of the distortion decreases with distance away from the dislocation line. So this magnitude is keep on reducing as we move further to this dislocation. Now because of this high strain in this region, dislocation line, this is also called dislocation pipe. In case of steel, there will be carbon is more likely to come and sit here, which will then again make a barrier for this dislocation movement. And this is the TEM of titanium alloy, which shows dislocations. Now these dislocations, these can be seen here because of the distance, atomic distance is different compared to so atomic distance will be different, which leads to the contrast, and it leads to that's why these dislocation regions are darker compared to other areas. Now there are two type of dislocations. First is edge dislocation and second is screw dislocation. There can be also mixed dislocation, which will be showing both of their character. Now dislocation line moves in direction of the applied shear stress, and in case of screw dislocation, dislocation line moves in the direction perpendicular to the applied shear stress. In case of edge dislocation, your the movement direction will be in this direction, and in case of screw dislocation, your shear stress direction is in this direction and your line movement is in this direction. The ultimate plastic deformation will be in this direction in both cases, in direction of shear stress. Now these are the Volterra dislocations. So Volterra was a scientist who gave these Volterra type of dislocations initially before even we saw dislocation under TEM. So he just told that these are the cylinders, hollow cylinders. So he cut one of the part and he shifted it along X direction, Y direction and Z direction. So which led to formation of edge dislocation, screw dislocation and disclination. Now stress required for slip. So previously we calculated what is the maximum stress that is required, theoretical shear stress that is required to move a lattice. So in this case it was GB upon 2 pi A, where B is your Burgers factor, A is your atomic distance. Now here shear stress required for slip by dislocation motion. So Pearls-Navarro stress, this stress comes out very lower compared to this theoretical shear strength. Now here what happens that we are not moving entire lattice compared to the lattice below, while we are just making an dislocation here. So there will be formation of dislocation like this. So previously your crystal was perfect like this. Now you are applying some shear stress at this side, so this plane will be inside this like this. So this system, okay, so now this plane has formed here, so it will start moving in this direction. Now we are these bonds and these bonds will be always formed, just one bond will be breaking and forming. So with that part won't require much energy as compared to what we earlier told in theoretical shear strength. In that part we totally broke these bonds and formed entire new row of the bonds. So that required a lot of energy compared to this one. So it comes out G upon 180, while in this case you got G upon 2 pi. So it is quite lower compared to theoretical shear strength. Here your B is dislocation width, so this also matters. So here your B, if width is higher, so width will be up to the distance of Burgess vector times 4. So this type of displacement should be there, so up to that we'll be counting the width of dislocation. This width will be very higher in case of metallic metals because these bonds are not very stiff as compared to in ceramics. So in ceramics this width will be quite narrow. That's what leads to increase in this shear stress, and which leads to higher strength in case of ceramics. Now in case of Burgess vector, so this is how your dislocation will move one step and forming a plastic deformation. Now Burgess vector, so for this in a perfect crystal, if you draw a loop like this, if we move 3 steps in this direction, 3 steps down and 4 steps this direction, 4 step this. So if we complete this loop without any addition of vector, then it will be perfect crystal. Inside this there is no type of dislocation or any other defect. While if we require addition of this Burgess vector, then there will be formation of a dislocation or another defect. Now this Burgess vector will be having direction to it and also magnitude to it. The magnitude and direction of lattice distortion associated with the dislocation is expressed in terms of a Burgess vector. So the nature of dislocation is defined by the relative orientation of the dislocation line and Burgess vector. Now for metals, the Burgess vector will point in a close peg direction with a magnitude equal to interatomic distance. And the dislocation density, so for various metals it is already given, like we can predict what it will be closer to. So dislocation density is your total length of dislocations per unit volume of material. So if a material is carefully solidified, then in that case 10 to the power 3 mm length of dislocations in per 1 mm cube of the crystal. And if it is heavily deformed metal, then 10 to the power 9 to 10 to the power 10 mm length of dislocations per unit of mm cube of crystal. Now characteristics of dislocations. So two dislocations having same sign and identical slip plane, they tend to repel each other. So here as we can see, so if a dislocation is like this, if half plane is above this, then there will be compressive force, and below there will be tensile force. So this is similar. So compressive is in upper part and tensile in lower part. So these will tend to repel each other. while if they are of different sign, then they'll be attracting, and this might lead to this type of system might lead to forming dislocation, annihilation. So when these dislocation will come closer, then they'll be forming a perfect crystal, so they'll be leaving no dislocation behind. And these dislocation might interact as well, so if they are at a particular angle, then there might be formation of different dislocation forest and etc. Now during plastic deformation, the dislocation density increases drastically. Now density in deformed metals is up to 10 to the power 10 per mm cube per mm square, and the strain fields and associated forces, they leads to strengthening mechanisms. Now slip systems and dislocations, they prefer to move in preferred planes known as slip planes along a preferred direction known as slip direction. So this is in case of FCC. So one type of planes have 3 directions to them. So these are 110 type of directions. So in these directions your slip will occur, and along these planes your slip will occur. Now these planes are always highly packed, and direction as well, they are highly packed directions. Now slip system is a combination of slip plane and slip direction, and the slip system depends on crystal structure. So for FCC there will be a particular slip system, and for BCC it will be different. The choice is such that the atomic distortion due to dislocation motion is minimum. For example, if your dislocation is moving along this direction, so there will be, this is the interplanar distance T1. So this T1 should be highest in case of easy glide, and the interatomic distance should be the lowest. Dislocations prefer to move in closely packed planes along closely packed direction, as the interatomic spacing in the plane is small. Consequently, the interplanar spacing is larger, easing the atomic motion. Now these are various slip planes and slip directions and their systems. Now for FCC there is 12 slip systems, and in case of BCC there can be up to 24, and in some cases there are 48 as well. In case of HCP there are 3 slip systems, so it makes them quite brittle compared to other systems. In case of PCC, at higher temperatures some slip systems, they become active, leading to easier glide at higher temperatures. So these metals BCC, they are worked at higher temperatures. Now Burgers vector for various systems. So Burgers vector denoted by B represents the dislocation slip direction, and the magnitude is equal to unit slip distance, which is interatomic separation in the direction. Now the direction and magnitude of B depends on crystal structure. So for B, A by 2 for the direction 110. In case of BCC it's 111 A by 2, and for HCP it is 112/0 A by 3. Slip in single crystals. So age, screw and mixed dislocations, they move in response to applied shear stress, and even the applied stress in tensile shear components, they exist at some alignments to the applied stress direction called resolved shear stress. Now resolved shear stress depends on the applied stress, orientation of slip plane and slip direction. The slip occurs when the shear stress acting in the slip direction exceeds a critical value. So from this there comes the Schmidt's law. So your uniaxial tensile stress is applied in this direction, and relative to that will be measuring phi and lambda. So phi will be tensile this stress axis versus normal to slip plane angle, and with slip direction it will be lambda. Now relating to that, your resolved shear stress can be given as your stress times tensile stress times cos phi and cos lambda. So this geometry of this tensile direction, it also affects uh, it also affects your initiation of plastic deformation. So Schmidt's law, it tells the value of tau r at the which slip at which slip occurs is a in a given material with specific dislocation density and purity is a constant, which is known as critical resolved shear stress. And the metallic single crystals have several slip systems, and the resolved shear stress may be different for each case. And generally, there will be one most favorably oriented system resulting in the largest resolved shear stress. Now, next is tilt boundary. Next is tilt boundary. So various degrees of crystallographic misalignment between adjacent grains is possible. So various degrees of crystallographic misalignment between adjacent grains is possible. So because of formation of these type of dislocation, there will be misalignment. This can be given as theta, and when the orientation mismatch is slight on the order of a few degrees, then the term small or low angle grain boundary is used if it is higher. So for example, it is given either relative to 5 degree or 10 degree. So if it is higher, then it will be large angle grain boundary or high angle grain boundary. So these boundaries can be described in terms of dislocation arrays. Now, one simple small angle grain boundary is formed when a edge dislocations are aligned in the manner of this type of is called a tilt boundary, and it can be called twist in case when there is screw dislocations are piled up. So here the angle of misorientation is called theta. Depending on this theta, your energy also changes. Twin boundaries. So a twin boundary is a special type of grain boundary across which there is specific mirror lattice symmetry. So on both of their side there are atoms present on mirror positions, and atoms on one side of the boundary are located in mirror image positions of the atoms on the other side. And the region of material which these boundaries is appropriately termed a twin. The twin results from an atomic displacement that are produced from either applied mechanical shear forces, which are called mechanical twins, and also during annealing heat treatments following deformation, which leads to annealing twins. Now, annealing twins are typically found in metals that have FCC type of crystal structure, whereas mechanical twins are observed in BCC and HCP type of metals. In copper, it is seen this type of annealing twins. Now, grain boundaries. So boundaries that are separating two grains or crystals having different crystallographic orientations in polycrystalline materials. So from this will have different orientation compared to this grain. So there will be grain boundaries. So these can be high angle grain boundary, they can be small angle grain boundary depending on misorientation. Now the atoms near the boundaries are slightly disordered and have higher energy than those within the grains. So when we try to look them below microscope, so for this we need to use etching. So for etching, we'll be putting some chemical on it, some acid. So these brown boundaries will get exposed to the acid and will get chemically attacked first. So these areas will look darker under the microscope like this one. and these form during solidification. As the nucleation rate is higher, then more of these like this, these nuclei will form initially having different orientation. Now these will keep on growing and will form these grain boundaries. When the growth is complete, these areas will be disordered. Other interfacial defects, so there can be stacking faults, in which case we saw earlier that in case of FCC there is ABC type of stacking sequence. So in some area there will be some layer will be missing, which might lead to formation of stacking sequence such as ABC, AB, CB. So this type of will lead to formation of HCP type of stacking sequence, or if there is HCP type of structure, then there can be formation of FCC type of stacking sequence. There can be phase boundaries as shown here. So this phase is different compared to this one, so it can be FCC and it can be BCC in a single material as well. Ferromagnetic and electric domain walls, so there will be a boundary separating different magnetic orientations. Or the atoms at the boundary are less regularly arranged or bonded, hence they will have higher energy. And we saw earlier, high angle grain boundaries will have high energy, low angle grain boundaries will have low energy, and grain boundaries are more chemically reactive due to their higher boundary energy. So impurity atoms, they are attached here due to their high energy state. Now 3D defects, so these are also called bulk or volume defects. These include pores, cracks, foreign inclusions and other phases. So they are normally introduced during the processing and fabrication step. So small vacancy cluster, void pores, these will be your 3D defects. Now various questions are asked from the strengthening mechanisms in your assignment. So there are various strengthening mechanisms. So here the ability of metal to plastically deform depends on the ability of dislocations to move. So dislocation will be moving and forming a slip step. So thus restricting or hindering dislocation motion makes a material harder and stronger. So some mechanisms to strengthen metals are as follows. First is grain refining. So we'll be reducing the size of grains. So that will lead to strengthening of material. Solid solution, strain hardening, precipitation strengthening, these all are explained further. Martensitic strengthening is formation of martensite in steels, and composite strengthening, we can form composites which will lead to strengthening of material. First is grain refining. So in this case, fine grained material, one that has small grains, is harder and stronger than a coarse grained material. So due to a greater total grain boundary area to restrict dislocation motion. So in this case we follow a Hall-Page equation. So below, in certain range of grain size, this type of trend is seen. So your yield strength equals to friction stress plus Ky, which is extent to which dislocation are piled up, divided by root D. D is your average grain size. So the critical grain size, which is typically around 10 nanometer, the yield strength would either remain constant or decrease with decreasing grain size. So this phenomena will be called inverse Hall-Page relation. So this equation is also not valid for very large grain size, and also not for extremely fine grains. Now grain boundary, they act as barrier to dislocation motion because two grains are at different orientation. So if a dislocation is passing into grain B, so if there are two grains as shown earlier, so from this to this, when it is passing dislocation, so it has to change its direction. So if we are applying force in this direction, then it is moving in that direction. Then at the grain boundary, it has to change its direction, which will require higher energy and higher stress. And atomic disorder within the grain boundary region will result in discontinuity of slip planes. So it leads to increase in strength. So if the grain size is decreasing in this direction, then yield strength is keep on increasing. Now grain refining, for high angle grain boundaries, the dislocation will not traverse across grain boundaries. So it is harder for this dislocation to go in another grain. And dislocation pileup will occur at the grain boundaries, and this pileup might lead to formation of another dislocation of opposite sign in adjacent grains. Now a fine grained material is harder and stronger compared to its coarse grained counterpart, and reduction in grain size will also lead to increase in toughness for some materials. Hall page strengthening limit. So up to certain, as I told earlier, in case of lesser than 10 nanometer size, there will be inverse Hall page relation. So this is the maximum attainable yield strength using grain boundary strengthening. So experiments on nanocrystalline material suggest that the yield strength, it starts to decrease with further reduction in grain size, and the phenomena is known as inverse Hall page. If the grain size drops below the equilibrium distance between dislocations, the Hall page relation breaks down. With the reduction in grain size, grains will be of the size of unit cell, which destroys long range order. So when we reduce grain diameter below 10 nanometer, so it won't be able to accommodate many dislocations, which will lead to there won't be formation of any dislocation pileup. So there won't be any strengthening. So in this case, your material will act as amorphous. Now second strengthening mechanism is solid solution strengthening. In this case, pure metals are almost always softer than their alloys. Adding another element that goes into interstitial or substitutional position in a solution increases strength. So as we can see, as copper amount will increase in nickel, your tensile strength will keep on increasing, while the elongation is your ductility, it will decrease. So the impurity atoms, they cause lattice strain, which can anchor dislocations. So it will interact with dislocations and will lead to increase in strength. So alloys are stronger. So as also seen in case of gold, so you can't use pure gold for making jewelry, so you use some impurities for making it stronger. Now like this, if we introduce some small atoms, then there will be impurities will exert tensile type of strain on the surrounding crystal, and if it is a larger in size, then it will exert a compressive type of strain. So alloying with impurity atoms that go into substitutional and interstitial locations, it improves strength and hardness, and high impurity metals usually softer and weaker than their base metal, and this I covered earlier. So alloys are stronger because of they are be imposing some lattice strain on surrounding host atoms, and this lattice field strain, they interact between dislocations, which leads to strengthening, and impurity atoms inhibit dislocation movement. Now these small atoms, they tend to go and sit at the above dislocations, because here we saw earlier there is compressive type of strain in this area. So if smaller atoms will be residing there, so less compressive strain will be there, and larger atoms, they tend to sit below dislocation line, so that to reduce this tensile type of strain. Now other strengthening mechanism is strain hardening or work hardening. In this case, we enhance strength with increased plastic deformation. So the strain hardening is the phenomena where a ductile metal becomes harder and stronger as it is plastically deformed and it is also called work hardening or cold working because the temperature at which deformation takes place is lower than the melting temperature, and the effects of the strain hardening may be removed by annealing heat treatment. So if there is very high strain hardening, so if we are working on metal, then in between we provide it annealing to reduce the uh, density of dislocation. This is in heat treatment. What we do, we slowly heat the material, then slowly cool. The strength increases but ductility is sacrificed. Plastic deformation and polycrystalline materials. So it is a complex deformation mechanism. These numerous grains and they have random crystallographic orientation. For each grain, motion occurs along the most favorable slip system. And the gross plastic deformation, it is distortion of individual grains. Now grain boundaries, they play a major role in hindering dislocations. Now for these two grains, they will be having different slip systems which will lead to formation of these are the slip steps that are formed in individual grains, while here these are slip lines. In case of polycrystals, so in single crystals, work hardening is due to dislocation interaction which impede the motion of dislocation, and interference of neighboring grains introduces the problem of compatible deformation among adjacent grains. Now multiple slip, hence work hardening at the very beginning occurs, and plastic deformation and associated work hardening increases dislocation density. As we saw earlier, it will be 10 to the power 12 meter of the dislocation length per meter cube of the crystal volume. Now this is how your dislocation density is your rho, tau is your shear stress required for slip. So this keep on increasing. So these are, if we increase the dislocation density, shear stress required will also increase. Now other strengthening mechanism is precipitation strengthening. There is one more which is dispersion strengthening. In that case, we'll be introducing some dispersoids which will be oxides or some ceramic particles in a metal matrix, which will lead to again dislocation will be hindered by those dispersoids, as we are seeing will be hindered by these precipitates that are forming here. So in case of precipitation hardening, firstly, it is technique used to increase the yield strength of malleable materials like aluminium copper alloys and stainless steels. Now based on changes in solid solubility with temperature to produce fine particles of an impurity phase which blocks the movement of dislocation in a crystal's lattice. Now alloys must be kept at elevated temperature for hours to allow precipitation to take place. This time delay is called aging. Now in this case, this type of phase diagram is required. So here in this alpha region, it is your complete solid solution. Now in this case, we have to take our material initially. So this is solute heat treatment. We'll be taking in this temperature range and making it single solid solution. Then we'll be cooling it in this region where there will be precipitate present. So for precipitation, firstly we'll be quenching it. So there will be solid solution at the room temperature as well. Then we need to heat it for precipitation to come out, which is known as precipitation heat treatment. Now here it is theta double prime phase, then it will lose coherency, then it will be theta phase particle. Initially there will be GP zones, so these are in nanometer size and these provide a lot of hardness, and this is for aluminium copper type of system. So it keeps on losing coherency, leading to less strength in the material. Now last time there was a query related to FCC stacking sequence, so I put the diagram here for easier imagination. So this is your A, B, C, A. So ABC type of stacking sequence was there in case of FCC. So you have to take these face atoms and corner atoms along with it for this plane. And in this case other planes will be there, but they are facing differently with each other. So like this there will be ABC type of stacking sequence, while in case of HCP, when we'll be taking in 001 direction, it will be AB type of stacking sequence. Now I'll be repeating your questions once again because all of you joined late. So for the first question, you have to identify all the favorable conditions for the formation of a substitutional solid solution. So these are your options. So difference in atomic radii between solute and solvent atoms should be less than 15%, or same crystal structure for the solute and solvent atoms, or greater difference in the electronegativity, or negligible difference in electronegativity of solute and solvent atoms. Only one statement is incorrect, which is greater difference in the electronegativity. So your solid solutions solubility is defined by the Hume-Rothery rules. So these are 4 rules. So first, there will be difference in the atomic radii between solute and solvent atom should be less than 15%, and crystal structure should be same for solute and solvent. So if both are FCC, for example copper and nickel both have FCC type of structure, and there should be negligible difference in electronegativity, so that there won't be any formation of intermetallic compounds. And metal should have more tendency to dissolve another metal when it has higher valency. Second question is, which is not a strengthening mechanism? Precipitation, work hardening, creep, and solid solution. Your answer will be creep. So the formation of precipitation leads to strengthening of material. Work hardening, as I told earlier, it leads to dislocation multiplication, leading to enhanced strength. Third is creep, which is a mechanism corresponding to softening of material at higher temperatures. Fourth is formation of solid solution also leads to strengthening of matrix metal. Third question is, which is not a 2D lattice defect? Your options are grain boundary, twin boundary, stacking faults, and voids. Your answer will be void, because void is a 3D type of defect. So grain boundary, twin boundary, twist boundary, stacking faults are 2D, while void, porosity, precipitates, they are 3D. Now what is the slip system for FCC crystal? So it will be 111 type of plane and 1 bar 0 type of direction, because they are close packed. And these two are for BCC, and last one is for HCP. Fifth is, which statement is incorrect? So grain refining reduces toughness, precipitation hardening requires solution, heat treatment, and aging, work hardening leads to dislocation multiplication, and presence of lattice strain interaction between dislocations and impurity atoms increases strength. The answer will be first one, because grain refining is the only strengthening mechanism which doesn't reduce toughness. And in case of precipitation hardening, we require quenching from single phase region, which is solution, heat treatment, and subsequent aging is required. And work hardening leads to dislocation multiplication, and because of formation of Frank-Reed source. And in the case of solid solution, the presence of solutes or impurity leads to lattice strains which react with dislocations, providing a barrier to easy glide, leading to strengthening. Sixth question is, identify all the correct statements. The magnitude of grain boundary energy decreases with orientation misalignment between neighboring grains. Grain boundaries are more chemically reactive than the grains. the total interfacial area is lower in coarse grained material than in fine grained materials. So middle two are correct. First statement is incorrect because the magnitude of grain boundary energy increases with orientation misalignment between neighboring grains, because with increasing theta your bond length will increase, which will lead to increase in energy. While we saw earlier, grain boundaries are more chemically reactive because they have higher energy, and they have, due to deviation of bond length from equilibrium, it's leading to high energy. And the total interfacial energy is lower in coarse grained materials than in fine grained materials because of less grain boundary area per unit volume. 7, you have to identify all the correct statements. So in a screw dislocation, the atoms distort along a dislocation line. In a screw dislocation, the dislocation line moves in the direction perpendicular to the applied shear stress. Screw dislocations impart shear, tensile and compressive strains in their vicinity, or a screw dislocation qualifies as an interfacial defect. Your answer will be upper two statements are correct. So these are incorrect because screw dislocation only imparts pure shear type of strain. There won't be any tensile and compressive stress components. And screw dislocation don't qualify as interfacial defect, but it qualifies as linear or 1D type of defect. An aluminium alloy has yield strength of 145 MPa. It has an average grain size of 2 micrometer, and the Hall constant depicting resistance to dislocation is 70 MPa. If the grain size is reduced to 100 nanometer, what will be the new yield strength based on Hall-Page relation? So your answer will be 405 MPa. So this is your Hall-Page relation. Sigma y equal to sigma naught plus ky t divided by root t. So this t is your grain size, sigma y is yield strength, sigma naught and ky are constants, and sigma naught is frictional stress opposing motion of dislocation, ky is extent to which dislocations are piled up. So this will depend on strain hardening. Now first, using the initial parameters, you have to find out value of ky. So ky we can get from this equation by 75 multiplied by root 2. Now sigma y we can calculate easily, 405 MPa. Ninth question is identify all the correct statements. First is dislocation moment is favorable on planes with highest planar density along the directions with highest linear density. Or second is HCP metals are less brittle than FCC and BCC crystals as they have fewer active slip systems. Deformation by twinning is usually accompanied by crystallographic reorientation or all of the above. So these two are correct. This one is wrong because fewer slip systems result in less plastic deformation in HCP crystal, and highest planar density leads to less lattice friction, which leads to easy dislocation movement, and twinning leads to crystallographic reorientation. In 10th question, you have to identify all the correct statements. So Hall-Page effect refers to strengthening by grain size reduction. The presence of lattice strain interaction between dislocations and impurity atoms increases the resistance to dislocation movement. The resistance to dislocation movement by other dislocations increases with the dislocation density, or all of the above. So your answer will be all of the above. All statements are correct. Now that's all. So if you have any query, you can ask. I'll be here till 5.